Let's do a few more examples of finding derivatives using what I often would refer to as the coefficient rule, or as I say, the coefficient passes through the derivative, it will not affect the results. So, looking at the next example, finding the derivative of negative 11x, well, again, negative 11 will not affect that derivative, so I could rewrite this as so. And the derivative of x is just 1. Again, by power rule, or that's another one I suggest just memorizing. And in general, one way that you can approach derivatives is you can always memorize specific derivatives to specific functions. But the point of the rules is to help us remember with certain cases, there's patterns, there's shortcuts to determining the outcome. And in this case, this is just going to give me 1. So negative 11 times 1 is just negative 11, and that is that. Or again, if we were using the power rule, this is x to the first power, 1 would drop down, and this would become x to the 0. X to the 0 disappears because that's just 1, and I would get, again, negative 11 times 1, which is negative 11. Now, looking at the next example, this is one where if you were to try to use the power rule, you might say, okay, this is 2 times 9 to the 1 power, but notice that there is no x in the denominator, so this does not fit the power rule definition, and therefore that will not work. But another way to think about this is 9 squared, that's clearly 81. This is a constant, and instead we should be using this rule. The derivative of a constant is always 0. So just a warning about using the power rule and using rules. Be careful, because sometimes the homework or whatever might try to trick you, but sometimes it's easy to overlook things like that. But the derivative of a number is always just 0, because it does not involve x itself. Now let's look at the next one. What's the derivative of 4 times the square root of x? Well, as I was talking about in a couple videos ago with roots, it's helpful to rewrite these using fractional notation. So this would be 4 times x to the 1/2 power. And now I can use the coefficient rule. Or again, as a shortcut, I can drop the power down and multiply by 4. That will just be 2. And then I subtract 1 from the power of x to the 1/2, which would be negative 1/2. And again, I could rewrite this as 2 over root x. And, that's kind of the prettiest form of that answer, because again, negative 1/2 means divide, and 1/2 power means square root. Let's do a few more. What if I had 5 over x squared? Again, step 1, rewrite this as a power. This would be 5 times x to the -2. Now I can drop the power. 5 times negative 2 is negative 10, and subtract 1. 10 times x to the -3. So really what I'm doing is I'm using these rules in conjunction with one another. I'm using the power rule alongside the coefficient rule. And it's easy to remember, well, this coefficient will just multiply into the power that drops through. Or again, I could rewrite that as negative 10 divided by x cubed. Looking at one more, I could drop this power down. Negative 1 times negative 3 would be positive 3. Subtracting 1 from negative 1 would be negative 2. So I would be left with 3 over x squared. This one involving a negative fraction. Again, the negative fraction will drop down. 3/4 times 8 would be negative 6. Subtracting 1 from 3/4 would be negative 7/4. So I'd be left with negative 6 divided by the 4th root of x to the 7th power. And one last one involving decimals. Again, the power will always drop down. 2 times 1.2 would be 2.4. Subtracting 1 from 1.2 would be 0.2. And there we have it. In the next video, this lecture series is getting quite long, so we're going to have to cut this off a little bit early and save some of this for next week. But the next rule that I want to cover is the sum and difference rule. What happens if I have a combination of terms? And ultimately what we're trying to work up towards is how do we find the derivative of polynomials and all the shortcuts involved in such examples.